All right, today we are talking about a massive leap forward in artificial intelligence. This isn't just a story about making AI bigger. It's about how it got so much smarter and so much more efficient. We're going to dive deep into EfficientNet-B0 and the revolution it kicked off.
So let's start with the question that really every single AI researcher on the planet was asking. How do you actually build a better, more accurate AI model? For a really long time, the answer seemed, well, kind of simple.
The old way was pretty much just brute force. The thinking was really straightforward. You want more accuracy? You just make the model bigger. That's it. More layers, more connections, more everything. You just throw more and more computing power at the problem and cross your fingers. But, as you can probably guess, this whole approach had a major flaw.
Yeah, this led straight into what we now call the bigger is better trap. See, just making these models bigger and better was leading to absolutely insane computational costs, and maybe even worse, the returns were diminishing fast. You could double the size of a model and only get a tiny fraction of a % of improvement. It just wasn't sustainable.
But then, in 2019, a team at Google AI hit the brakes. They looked at this whole situation and asked a truly game-changing question. Instead of just using brute force, was there a smarter, more principled way to grow an AI model? And that question, right there, was the spark that lit the EfficientNet fire. And this led to a completely new philosophy. You know, think about it like building a high-performance race car. You can't just drop a gigantic engine into a normal car and expect it to be a world beater, right? No way. You also need to upgrade the brakes, you need a stronger chassis, better aerodynamics. It's about upgrading the entire system in a balanced, intelligent way. That was the new idea.
An AI in a balanced way. Well, the researchers identified 3 key knobs that you can turn. First, you've got depth, which is just how many layers the network has. Then there's width. That's how many channels or neurons are packed into each of those layers. And finally, you have resolution, the size of the image you're actually feeding into the network. The old way was to just crank one of these knobs to the max. The new way was all about finding the perfect balance between all 3.
And they gave this secret sauce a name: compound scaling. So instead of just making a network way deeper or way wider or feeding it giant images, they created a mathematical principle to scale all 3 of those dimensions together in perfect harmony. It's a really elegant idea when you think about it. A balanced model is an efficient model. And that is how you get the absolute most bang for your computational buck.
Let's get into the nitty-gritty. Let's pop the hood on this baseline model, EfficientNet-B0, and see what's really making it tick. What are the actual building blocks that make this new approach work so incredibly well?
Now, here's a fact that is just wild. The core architecture, the B0 model itself, wasn't painstakingly designed by a team of humans over months and months. Nope. It was actually discovered by another AI. They use this technique called neural architecture search, which is basically unleashing an AI algorithm to hunt for the most efficient and powerful base design. So, in a way, AI literally helped design a better AI. How cool is that?
And the architecture it found was a combination of 3 key ingredients. First up, you've got these MB-conv blocks. Think of them like super smart, super efficient Lego bricks for building the network. They're designed to be really powerful but use very little computational energy. Second, it used something called the swish activation function. This is kind of like a smoother, dimmer switch for the AI's neurons, which helps it learn more effectively than a simple on-off switch. And finally, squeeze and excitation blocks. These things give the network a sense of focus, so it can pay more attention to the important parts of an image and just ignore the background noise. Put those 3 together, and you've got an incredibly powerful yet lightweight foundation.
All right, so we've got a new philosophy and we've got a brand new architecture. But the big question is, does it actually work? Well, let's take a look at the data, because the proof is right there in the performance numbers.
And this is the mic drop moment. Just look at this comparison. EfficientNet-B0 has about 5.3 million parameters. A classic, respected model like ResNet-50, way more. Now look at flops. That's basically a measure of how expensive it is to run. Again, EfficientNet-B0 is just vastly cheaper. And here's the kicker. It does all of this while delivering similar, and in a lot of cases, better accuracy. Less cost, less size, same or better results. I mean, it was just a massive, undeniable win.
And to put a specific number on it, EfficientNet-B0 hits 77.1% top 1 accuracy on the ImageNet benchmark, which is basically the Olympics for computer vision models. At that time, hitting that level of performance with a model this small and this efficient, that was a genuine breakthrough for the entire field.
So this is all great for the researchers, but what does this breakthrough actually mean outside of the lab? Let's look at how this incredible efficiency translates into the real world, because this isn't just some academic paper. This efficiency has unlocked some amazing applications that you might even be using every single day.
Because it's so lightweight, it can run on things like mobile devices. So just imagine a farmer out in the field who can just take out their phone, snap a picture of a crop, and instantly get a diagnosis on a potential disease. That's the kind of thing that's made possible by this kind of efficiency.
Or how about in healthcare? Its high accuracy and speed are perfect for analyzing medical scans like X-rays. It can act as this powerful assistant for doctors, helping them spot potential problems faster and with more accuracy than ever before.
And yep, this is exactly the kind of technology that powers features on your smartphone. Its ability to run super fast and accurately on a low-power device makes it absolutely perfect for things like facial recognition to unlock your phone.
And it goes way beyond just saying, this is a cat. EfficientNet is so good at understanding visual information that it's now used as the foundational backbone. You can think of it as the visual cortex for much more complex AIs that can identify and even outline dozens of different objects all within the same scene.
So let's bring this all together. Why was EfficientNet more than just another good model? Why are we calling this an entire revolution?
Because ultimately, this was about so much more than a single piece of code. It fundamentally changed the goalposts for the entire AI community. It was the moment the field shifted away from that brute force idea of bigger is better and toward a new, much more elegant paradigm. Smarter is better.
Its legacy today is crystal clear. First, it proved, without a doubt, that a balanced, principled approach to scaling is just flat-out superior to just making things bigger. Second, it unlocked the power of high-end AI for all the devices that don't have supercomputer-level power, like the phone in your pocket. And finally, it helped push the entire field towards a future of building more sustainable and more accessible AI for everyone.
And that kind of leaves us with one last big thought to chew on. Now that we know that efficiency is a kind of superpower for AI, allowing it to go anywhere and do more with less, what are the massive real-world challenges that we can finally solve next?